One of the basic principles we learned in lab was that the amount of work done to stretch a spring is stored in the spring as kinetic energy, or not as kinetic energy, sorry, as elastic potential energy, and we know Hooke laws, how to use Hooke laws to figure out force and work in a spring. So let's just work an example problem real quick. A lot of the things that we do to weigh things are actually based on Hooke's law. We have a spring scale which actually has a little spring in it, and then we put a hook on the end of that, and then we hang stuff off of it. Okay, and these two things balance out. So if this is hanging on the end of a scale, let's say this thing has a mass of 5 kilograms. There are two forces acting on it. There's the force pulling up, and this is the force from the spring, so I'm going to call it F spring. And then this is the force due to gravity, Fg, pulling down. Okay, since the spring scale stops pulling when these two, or stops stretching when these two things are at rest, if we know how far this spring has moved, we can figure out the spring constant. Or if we know the spring constant, we can figure out how far it moved. So let's say when we put this 5 kilogram mass on there, it stretches the spring over a distance of 8 centimeters. I want to know the spring constant of the spring. So to do that, all we do is we say, well, Hooke's law says the force in a spring is equal to the spring constant K times the distance it stretches, x. And the force that I have here, well, is going to be equal to the force due to gravity, because according to Newton's second law, net force is equal to mass times acceleration, and in the y direction, it's not accelerating, it's 0. So I have F spring minus Fg is 0, so Fs equals Fg, and we remember from every time, mass times the acceleration due to gravity is that force. So 5 times 9.8 equals 49 newtons. So this is a 49 newton force pulling down, which means this is a 49 newton force pulling up. So I'm going to use that in this equation. 49 equals K times, this is 8 centimeters. I want this in meters, so 0.08 meters. Divide 49 by 0.09, and we get, or sorry, not 0.09, 0.08, and we get 612.5. So K is 612.5, that's newtons per meter. Okay? So it takes 612 newtons of force to stretch the spring a meter, and every meter we stretch, it's going to go that much further. So I want to know how much work was done by gravity to stretch this spring. Okay? So if I want to know that, work is equal to force times distance. But can I just actually use that force and that distance? Okay? Can I use this force in the spring? Well, it turns out I can't use the 612.5 newtons, or sorry, the 49 newtons of force, because that force isn't constant. Remember from lab, that force in the spring is constantly going up. The more you stretch it, the more force is required. So what we had to do was we had to say, actually the work done to stretch the spring was equal to 1/2 the spring constant times the distance you pulled it squared, because kx gets you, right, the slope of this line, f equals kx, and over here I have f, down here I have x, so the height is kx, the base is x, so f equals kx gets me the height. I multiply that by x for the base, and half base times height for the area of a triangle, so 1/2 kx squared is the work done to stretch a spring. Now that I have the spring constant, I can figure that out. I couldn't just use this because the force wasn't constant. So now I have 1/2 times 612.5 times that 0.08 squared. And when I do that, 612.5 times 0.08 squared, and divide it by 2, I see that I've only done 1.96, or gravity's only done 1.96 joules of work. So that's how much energy is actually stored in the spring, 1.96 joules. Okay? That's elastic potential energy. So these problems don't really get too tricky. You just got to remember, because the force is varying as the spring stretches, we don't just use the force times distance equation to get work. We use the 1/2 kx squared to get work. And because work is the transfer of energy, the work done to stretch a spring is equal to the energy stored in the spring.